Hello everyone and welcome to another Stat 437 lecture video. In today's video we're going to be actually taking a look at how we're going to implement linear marginal models using R. So we're going to take a look at the TLC data, which we've been using as an example, and we're going to try to fit some models and discuss how we're going to go about testing hypotheses and sort of getting a feel for how these models work in the real world and sort of discuss some of the things you should be looking out for. So with that, I'll open up our studio here. So the first thing to note is that I have the TLC data and the conversion of it into long and wide form already sort of typed out here. So I have to set my session to be the correct location, but then should be able to load that all in. And so that is all from the first video where we're actually exploring this data. So go watch that lecture video if you're not sure about conversion between long and wide format. But once we have this loaded in, then we can actually take a look at fitting some of these models. And so generally speaking, what we're going to be doing is using a package called nlme. Okay, so I have it built and loaded here, so I can just call library and load it in. If you haven't installed it, you can call install packages and then type nlme, and that will, running that command will install the package for you. So I'm going to assume that you have it installed. And in particular, we're most concerned with one function in it called GLS. So if I type $GLS and I run that, you can see it pulls up the documentation here in RStudio. It would do the same thing in the terminal. And you can see that we're going to be able to fit linear models using generalized least squares, which is exactly the method that we've been talking about for fitting linear marginal models. So it's used using generalized least squares. And you can come down and you can sort of dig through this documentation as you need to get a feel for what the function is doing. We're going to be in particular looking at a handful of different parameter or options here to the function call. So the correlation will allow us to specify the correlation pattern that we care about. These weights are going to let us specify the variance patterns that we care about. And the method is going to either be based on restricted maximum likelihood or maximum likelihood. So if you don't know the difference between those two, that was discussed in the previous lecture video. And so we're going to be able to control all of that using this GLS function here. So to begin, I just want to fit sort of a saturated model based on our TLC data here. And so what I'm going to actually do is take a look at the long data file that we have open. So I'll view TLC long here. And you can see that it's a data frame, and we've seen this before, so it shouldn't be new, but each row here is corresponding to an individual observation from one individual. So we have the ID, and then we have whether they were on a placebo or an active treatment. We have the week, which is going to be a number either 0, 1, 4, or 6. And then we have W, which is the actual lead level measurement from their blood at the corresponding time point. Right, and so if I sort by ID here, each patient in this data frame will have 4 rows for them. So ID1 has 4 rows. And so this ID captures which individual it is. This week captures which week number it is. And then the W is the actual outcome that we care about. And so generally speaking, we want to fit a model that explains W with respect to week and treatment. And so let's see how we can go about doing that. So I'm going to fit a saturated model first. And so I'll call this model saturated. And we're going to be using the GLS function. And so the first thing that we want to specify is model. And model is going to be a formula, an R formula, that specifies what the actual model that we're fitting here is, just like you would use in LM or GLM. And so in our case, we were saying that we want to fit W based on week and treatment. And so I'm going to come in here and I'm going to go W, and it's going to be week interacting with treatment. And so this is going to include the treatment and its interaction with week. Now, what I actually want to do is wrap week in a factor variable. And the reason is that right now it's numeric. It's going to be 0, 1, 4, and 6. And so if you wanted to treat that as a continuous factor, you could do that just by including week directly. But instead, because we only have 4 time points, it's only going to take 3 parameters to fit the main effects and then an additional 3 to fit the interaction with treatment. And so that's not that many parameters based on the 400 rows that we have in our data. So I'm going to use a factor variable instead. Now, we talked a lot about whether you want to use time as a continuous variable or as a factor variable in the previous lectures. And so, that's a choice that we can make, and we could see what the impact is later on if we're depending on how this lecture is going. But for now, we're going to use it as a factor and treatment and crossed with treatment. And so this is going to give the model here. Okay, and so that's specified exactly the same way that you would in GLM or LM. The next piece that we want to specify is the data. Now this is expecting a long data frame, right? So we'll pass in TLC long here, nothing too special going on. Next, we want to specify the correlation. Okay, and so I'll specify correlation equals, and then this is going to take a little bit of getting used to the exact form that you want to specify here. So if I pull back up the documentation and I scroll down to correlation here, you can see that it is expecting a core struct object, and it says, see the documentation of core classes for a description. So if I click on this here, we've pulled up this correlation structure classes documentation. And each one of these is a different correlation pattern matrix that you could possibly specify. So in that lecture that we were talking about it, we talked about sort of a symmetric correlation matrix that had no other structure imposed on it. So the sort of the unconstrained matrix. So you can see that that's specified as core sim here. We also talked about a compound symmetry matrix, which corresponds to the constant correlation. So it's one correlation parameter for the whole value. We talked about autoregressive correlation patterns, so that's core AR1. We talked about the exponential correlation structure and the Gaussian correlation structure. And so all of these are sort of available to specify here, right? And so this documentation is there for you to dig through. But generally speaking, what you're going to want to do is you're going to pick out which structure you want to use. So for now, I'll use the unconstrained, which is called core sim here. So we'll go core sim, and this is actually a function call. And what we have to do is specify the form. And so the form is going to be a formula as well. And in general, the formula is going to tell you what factors you want to use to explain this correlation. Now, for us, we just want to fit a correlation for within each individual, right? So what I'm going to do is I'm going to define my formula to be tilde1. So this tilde1 is saying we don't need to use any of the variates to explain this correlation. And then what I'm going to do is I'm going to use this pipe here, so just a straight vertical bar, and then I'm going to type ID. And just like in an expectation or probability notation, if you have the pipe, it tells you that you're conditioning on whatever comes after it, right? So too with the formulas here. So what we're basically saying is that the correlation we want to be conditioned on the ID, or in other words, we want to compute these correlations within each person. Okay, so that's going to be the formula. It doesn't require any other covariates, but we do want it to be within the individual. All right, so I'd encourage you to play around a little bit with that, but generally speaking, you're going to pass in this form right here, and the ID variable is just going to be whatever the ID is in the data, and that's going to be what we're doing for this course, but you can get a little bit more complicated with that. The next piece that we want to pass in is weights. Now, weights in general are going to specify the variance patterns. So we had talked about making the assumption of constant variance when we were first introducing the marginal linear models, but then we discussed a little bit about why that might not be the most appropriate version. And so we also talked about, say, fitting a different variance parameter at each time point, right? And so then in this case, instead of having one variance, we would have 4 variance terms, one for each of the different time points. Okay? And so just like with correlation, the variance is going to be specified by specifying a form. And in particular for us, we're going to use this var ident function, okay? And then we need to specify the form. And so again, my form is going to be $1 because I'm not letting variance change based on any covariates, but then we need to nest it inside of something. And in our case, we're saying we want to fit a different variance parameter for each week. And because we were using factor of week up here, we should use factor of week here. And so these two sort of forms are going to be acting similarly. The correlations are within the individual, specified by ID, and the variances change over the weeks, so specified by factor week. The last thing that we want to change here is we can specify the method. And the method is either going to be maximum likelihood or restricted maximum likelihood, depending on what our goals are with this. So for now, I'm going to fit the maximum using maximum likelihood, but we had a discussion of using restricted maximum likelihood in the last lecture. And so we'll see that sort of later on. And it's going to be just as simple as changing method from maximum likelihood to restricted maximum likelihood. Okay, so with this, that's everything we need to specify. And so I can simply run that function there. Takes a second, but then we can see that the model has actually fit. And so if I call summary on model saturated, then we're going to get a bunch of output. And I'll sort of scroll all the way up to see. So you can see that we fit it by maximum likelihood. We have our actual model that we're fitting, and then we have some first general fit assessment criteria here. So we're given the log likelihood value. Recall that if we're using restricted maximum likelihood, we're not actually using the log likelihood, and so it's not going to be exactly useful there. But for now, this log likelihood is there, and we could use it. We're then given information about the correlation structure. So we're using a general correlation structure, and we can see down here, we actually estimate this correlation matrix. Now we know it's symmetric and correlations with themselves are always 1, and so we only need the lower half of the matrix here. We can see the correlation between weeks 1 and, between weeks 1 and 2 is going to be 0.571. Between the first and fourth week is going to be 0.570. Between the first and sixth week is 0.577, and so on throughout this correlation matrix. So if we have questions about the correlation structure, we can ask them based on sort of this output here. We then get information about our estimated variance structure. So we're estimating different variances within each week, right? And you can see that we get these parameter estimates right here. So we've estimated 4 of them for 0, 1, 4, and 6, right? We can then scroll down a little bit more and we can see that we get different coefficient outputs here, right? So this is our standard table of coefficients where we are estimating the value and the standard error. And then we get a t-statistic, which is just the value divided by the standard error. And then the p-value, which is just the hypothesis test of this value equals 0, right? So you can quickly look and see that, for instance, treatment's main effect doesn't appear to be significant, but the interaction of treatment with the weeks does appear to be significant. And so, you can sort of just get an overview of the different model parameters there. And so that's generally speaking what we're going to be focusing on. And so with that first model fit, we can start asking some questions, right? So first, we might be interested in asking about this correlation structure that we specified, right? We talked about the unconstrained correlation being sort of a lot of parameters potentially. And, we might wonder, well, do we even need to use all of those different parameters, right? And so if we take a look at this correlation matrix that has been estimated here, you can see that for the most part, the correlations look roughly constant, right? So we have 0.57, 0.57, 0.58, 0.58, 0.58, and then there's this 0.775. And so this might be sort of different, substantially different from the other correlations, but perhaps not. And so, there might be a question of, do we actually need to be using an unconstrained correlation pattern here? And so this is something that we could actually, fit a model and test. And so what I'm going to do is I'm going to say, let's fit a compound symmetry model here. So I'll call this model compound symmetry, and I'm going to copy and paste this code exactly. But instead of calling core sim, I'm going to call core comp sim. Okay, and you can run this code here, and I can call summary on the model compound symmetry. And if we take a look at the correlation output, you can now see that we get a single correlation estimate. So it's 0.61, right? And so that's sort of between that 0.57, 0.58, and that 0.775 that we had estimated before, right? And so is this reasonable? Well, we can actually formally test that. We don't have to eyeball whether or not this seems reasonable. And so in order to do this, I want to remind you all of the likelihood ratio test. So if I pull open my whiteboard here just for a moment, we can see that I have what's written down here is the likelihood ratio test statistic, okay? And this should have been shown to you in your GLM course and perhaps in other courses as well. But the basic idea is that if we take, if we're interested in a null hypothesis where we're taking some parameter that we care about, theta equals to theta naught, okay? Then if we take the log likelihood at theta naught and we subtract off the log likelihood at our MLE, a theta hat, and if we do -2 times by this value, right, then as long as our constrained likelihood sort of fits within this parameter space of our maximum likelihood, this is going to follow a chi-squared distribution, where the number of degrees of freedoms is the number of constraints that we're putting on theta naught. Okay, and so if we think about what we're actually doing for a second with the compound symmetry assumption here, right? We have this correlation matrix that we talked about as R of rho, right? And in the unconstrained case, what we're letting this be is this matrix that's going to have a 1 on the diagonal, and then it'll have row 1, 2, row 1, 3, row 1, 4, and then it'll have another 1, another 1, another 1, just fill those in. And then we're going to have row 2, 3, row 2, 4, and here we're going to have row 3, 4, right? And so, and then it's going to be symmetric, right? Same thing down here. And so this is the unconstrained version. If we assume compound symmetry, then what we're assuming is that R of P is equal to, again, we have 1s on the diagonals, but then we just have one row for all of these spots, right? And so in some sense, if you think about how are we getting from this unconstrained matrix down to this compound symmetry matrix, well, what we're saying is we want row 1, 2 equals row 2, 2, row 1, 3 equals row 1, 4 equals row 2, 3 equals row 2, 4 equals row 3, 4, right? And so by constraining the parameter space here, we can get from our unconstrained model down to our constrained model down here. And so we would say that the compound symmetry assumption is nested within the unconstrained model that we started with, right? And because of that, because we have this nesting of models, all that we're doing to get to this sort of more constrained version is restricting the parameter space, and so we can use a likelihood ratio test. Now, we could, of course, actually compute this based on the values that are output here. The other way that we could do it is by using the ANOVA function in R. So I want to show you very quickly sort of both ways, because this is a very useful technique for working here. But the things that I want to point out first is we can take a peek first at the degrees of freedom down here, right? And so you can see that we have 392 degrees of freedom for the compound symmetry. And then so we've reported these 392 degrees of freedom here, and we also see that there's this reported 392 degrees of freedom up here. Now, this is going to be something that you have to be slightly careful with, because if we're just thinking about it sort of logically, right, the compound symmetry assumption here is only estimating a single row parameter. The saturated model is estimating 6 row parameters, right? And so if we're estimating 5 additional parameters from our data, we shouldn't end up with the same number of degrees of freedom. And so you have to be careful when you're looking at this output the way that you may have from a GLM or an LM, where reading off the residual degrees of freedom is not going to work exactly. So how can we do this instead? Well, if we actually take a look here at a call, so if we call ANOVA And ANOVA is going to take a couple of different objects. So for us, we're going to pass in ANOVA of the compound symmetry model, and we're also going to pass in the saturated model. Doesn't matter which order you pass this in. If I run this call here, you can see that we get this output here where we have our two models, model 1, model 2, and you can see now that we have these degrees of freedom listed where there's 13 versus 18, right? And so there's that difference of 5. We've estimated 5 additional parameters for the compound symmetry. So we've used up 5 more degrees of freedom. And our question is that going to be a sort of a significant difference? So under the likelihood ratio test that we're doing here, so this here has done sort of our likelihood ratio test directly for us, right? And so we can see that we get the test of 1 versus 2, so model 1 being compound symmetry, model 2 being the saturated, is going to give us a p-value of 0.0026, right? And so this is probably at the point where we would reject the null hypothesis. And so in this case, our null hypothesis is that all of those row parameter values are equal, right? And so this probably gives us evidence that the compound symmetry actually does improve over that the saturated model really does improve over the compound symmetry. Now we could take a peek at this sort of doing this directly as well. Okay, so if we recall that test statistic for the likelihood ratio test is -2 times by the difference in log likelihoods. And so if I take my model compound symmetry here, I can grab the log lik, so $LOG-LIK, and I can subtract off the model saturated log lik for the log likelihood. And if I just run this, you can see that I get 18.24948, right? Which is exactly the same L ratio value that we saw in the ANOVA call here, right? And so then right there, we're saying that the degrees of freedom are 3, which does appear to be incorrectly computed to me. Since in actual fact, we're looking at 5 constraints, right? And so if instead of that, we use 5 degrees of freedom, you can see we get this 0.0026 value there. So I'm not sure why we're seeing a degrees of freedom equals 3 there, but in any event, we can get the same p-value by looking at those models directly. So that's the likelihood ratio test there. And so really what we're saying here is that the compound symmetry assumption probably shouldn't be made here, that the saturated model is actually going to be substantially better. So just to quickly run over what it is that we just did here, we tested the correlation pattern by fitting a model with the nested correlation pattern, right? So compound symmetry is nested within this unconstrained version. And then we used a likelihood ratio test, either using just this ANOVA call here, or we figured out how to compute directly using the log likelihood values computed from the GLS fit, right? And so you could think about doing this with sort of any 2 nested correlation patterns, but the same thing is going to be true of other nested problems as well, right? So you could think about, instead of using the compound symmetry here, right, if we come down and we make this the symmetric, the unconstrained as well, what if we didn't nest the variance, right? So if we didn't compute variance, and so this is going to be a constant variance, right? So we're not allowing this to change over each week, right? So you could think about asking the question then, is a constant variance acceptable? And if you wanted to get a sense, well, does the constant variance seem acceptable? We can take a look at the output from the saturated model here. And you can see that we have these estimated variance parameters here. And, you can judge, to me, these look like they're probably substantially different from one another. But, if you're not comfortable making that judgment call yourself, you could fit this model constant variance. And now you should think about the fact that this constant variance is nested inside of that the saturated model that we initially fit, because we can get to it by just constraining each of those variance parameters to be equal, right? So that's 3 constraints in the model. And so if we come in here and we call ANOVA on the model constant variance, and we're testing that against the model saturated, right? You can see that we have 15 versus 18, so that's where that 3 constraints is coming from. And you can see that the p-value in this case is substantially less than 0.0001. And so again, the saturated model is fitting the data substantially better in this situation, right? And you could ask these same types of questions for other choices for the variance patterns or the correlation patterns, and as long as they're nested, we can work this way. If they're not nested, then we can't perform these formal tests, and instead we would want to just take a peek at these AIC and BIC values and see if they're sort of substantially changing. So as a general rule, you want lower AIC and you want lower BIC values, and so if it looks like there's been sort of a substantial drop, then you would say that the one with the substantially lower is better. Now, one important consideration, whenever we're doing these nested tests, you have to specify this as ML rather than restricted maximum likelihood, because this isn't going to compute the correct likelihood value, right? And so you can't use the likelihood ratio test if you're not using the maximum likelihood estimation form to do these sort of nested structures. Now, the other piece, other than testing our correlation and our variance structures that we sort of care about, is testing the parameters. And so in order to think about sort of hypothesis testing of these parameters here, we can sort of do one of 2 things, right? So we can do it in the way we were just thinking about it in terms of these nested models, or we can do it in terms of the asymptotic distributions that we were looking at before. But in order to sort of ask any questions of this model, it's probably first thinking about the parameter interpretation, okay? So if I just take a look at our saturated model right here, okay, so if I've just called coef on the model saturated, what this is going to do is just output all of these different coefficients, right? So the intercept is 26.54, the factor of week 1 is negative 13.08, and so on. And actually, in order to do this, what I'm going to do is I'm going to open back up my whiteboard over here. And so we can come here and we can sort of start to think about what these different parameter values actually mean, right? So in our saturated model, we fit 8 different coefficients, okay? And so what we have is we have beta 0, which is our intercept, and then we have beta 1, and I'm going to call this T1 plus beta 2 T2 plus beta 3 T3. And these right here are the main effects of time. And then we have beta 4, and I'll say treatment, TRT. Okay. And then we have the interaction effects. And so I will add these on as well. So we're going to have beta 5, and this is going to be T1 treatment plus beta 6 T2 treatment plus beta 7 T3 treatment. Okay, and so that's sort of our full set of parameters here. And we're thinking about these T1, T2, T3 as indicator variables, where T1 is going to be a 1 if it is week 1, T2 is a 1 if it's week 4, T3 is a 1 if it's week 6, right? And so then for any individual observation, exactly, or at most, one of these will take on a value of 1. And if all of them are values of 0, then we're looking at week 0. Okay. Now the treatment is also a binary indicator, where it's going to be either a 1 or a 0. It's going to be a 1 if they're in the placebo group, 1 if it's P, and it will be a 0 if it's active. And so then we can start thinking about the actual interpretations of any of these parameters using that rationale, right? And so there's sort of going to be a bunch of different combinations that we can think about here, right? So you can be at active treatment with week 0, with week 1, with week 4, with week 6, or you can be the placebo treatment at week 0, at week 1, at week 4, or at week 6. And then each of these combinations is going to include a different set of parameters. So active treatment, recall that treatment is going to be 0, and so in the case that we're receiving the active treatment, everything down here is going to be zeroed out. And so we're just going to have some combination of the initial parameters there. So we're going to have beta 0. At week 1, T1 is 1. So we're going to have beta 0 plus beta 1. At week 4, T2 is 1. So we'll have beta 0 plus beta 2. And then at week 6, we're going to have T3 being 1. So then we'll have plus B3, beta 3. Okay, now we can do a similar thing down for the treatment indicator being the placebo, but now we're going to always have this beta 4 term because treatment is 1, and we're also going to have interaction terms depending on which week it is. Okay, so here we're going to look at beta 0 plus beta 4, but all of these interaction terms are 0, right? And then we're going to have beta 0 plus beta 4 plus beta 5 during week 1. And then we're going to have beta 0 plus beta, oh, and in fact, I missed a term there, right? So at week 1, we're also going to have beta 1. So plus beta 5 plus beta 1, sorry. Then we're going to have beta 0 plus beta 4 plus beta 2 plus beta 6. And then for this last term, we're going to have beta 0 plus beta 4 plus beta 3 plus beta 7. Okay? And so we can sort of think about dividing these into two different parts for each of them. So we can see that we always have this intercept term, right? And so for the first 4, their baseline values are going to be just the intercept. For the people who are receiving the placebo treatment, we're thinking of their baseline as being beta 0 plus beta 4, right? And so what this means is that this beta 4 term is sort of capturing the effect of treatment where we're not including, or placebo treatment in particular, where we're not including sort of the time effect that we have there. Then we can think about the rest of these terms, so this beta 1, this beta 2, this beta 3, and then beta 5 plus 1, beta 2 plus 6, beta 3 plus 7 as being the effects of time on the variable here, right? And so one way to start thinking about what the interpretation of these parameters are is if we take a look at a person who is in this row versus this row. So it's the active treatment, or the placebo treatment, and the active treatment at week 0. If we take the difference in their expected outcomes, you can see that we're left with beta 0 plus beta 4 minus beta 0. So beta 0 plus beta 4. We subtract off beta 0, and we're left with just beta 4. And so the only difference between a person in this row and a person in this row is that in the bottom row here, the person was receiving the placebo treatment, and in the top row, they were receiving the active treatment. So then what we say is beta 4 is the expected change in the week 0 outcome of a person who goes from receiving the active treatment to the placebo treatment, and so on. Okay? And so we can start to think about sort of any combination of these parameter values, but what becomes most interesting to us as a general rule is asking questions about sort of the overall significance of, say, time trends. Okay, so if we want to know, for instance, are the patterns of change the same between the two groups over time? So in that case, what we're looking at is whether beta 5 equals beta 6 equals beta 7 equals 0. So we'll say B5 equals B6 equals B7 equals 0, right? And the reason for this, and perhaps I should pop back into the whiteboard just for a quick second. If beta 5, so I'll highlight the values we're talking about here. If we have beta 5 equals beta 6 equals beta 7, and all of those are 0, right, then what we would find is that the time trends between the groups are always going to be the same. So that's not to say that the groups are going to be exactly the same overall, but let's actually take a look at what would happen in that case, right? So if we zero out those factors, so I'll just cross those out here, right? And now if we think about at week 0, the difference between placebo and active is going to be beta 4, right? Beta 0 plus beta 4 minus beta 0, well, that's just beta 4. Okay, at week 1, if we have that term zeroed out, now we're going to have beta 1 plus beta 0 plus beta 4 minus beta 0 plus beta 1. Well, the beta 0, beta 1 both cancel out, and we're left with just beta 4 again, right? And so what that means is that if all of those terms that we just pointed out are 0, then the difference is always going to be this constant beta 4, right? And so that would mean that the time trends are exactly the same between those two groups. So I hope that makes some sense. We can come back into R here. And we can actually think about testing this hypothesis. Now there's going to be a couple of different ways of testing it, and I will show you sort of the two most obvious ways of doing this, and then from there you should sort of have this good sense of how we can go about using these values. So the first way, and perhaps the most natural way, is to actually just fit a reduced model. Okay, and so we saw that we had the saturated model, right? Just to remind you, I'll keep that there. But if I fit a model reduced, and I'm going to come back up to my saturated model and just copy and paste my GLS code here, right? Because what we're doing is we're constraining a few of these parameters to be equal to 0, this is the same thing as fitting a nested model, right? So instead of including the interaction, if we just include the main effects here, then what we're doing is exactly what we just discussed. And so we keep the rest of it the same. We fit this, and I guess I called it model reduce. So I'll come in here, I can say summary model reduce. And you can see that we're still fitting the same correlation structure, right? The values are different now, but that's to be expected. We're getting similar estimates for the variance, but now we don't have those values for beta 5, beta 6, beta 7. We just have beta 0, beta 1, beta 2, beta 3, and beta 4, right? And so those have been zeroed out. And now we can do the exact same test where we either use our ANOVA call or our log likelihood call. And so I'll just come in and do ANOVA model reduce and then model saturated. And if we call that, you can see that we're testing. Again, it makes sense that we have 3 degrees of freedom difference because there are 3 constraints. And you can see the p-value is substantially less than 0.001. And so what that's suggesting is that, in fact, those time trends are significant. Now, we sort of saw that when we looked at the summary of the model saturated to begin, and we just looked at the coefficients table here, right? All of these parameters look to be fairly significant, and so we would expect that, but it's nice to actually have a formal test of this. Now, the other way that we could go about doing this is using those L matrices that we talked about before, right? And so if we want to test this parameter of beta 5 equals beta 6 equals beta 7 equals 0, this is the same as beta 5 equals 0, beta 6 equals 0, and beta 7 equals 0, right? And so if we define an L matrix that corresponds to this hypothesis here, this compound hypothesis, then we can use those asymptotic results that we were talking about. And so the way that we're going to do this in R is we're going to call an R bind, and this is just going to take a bunch of vectors and combine them into rows. And each of these rows is going to just select out a single parameter. And so I'm going to copy and paste this in so that I get the correct number here. But so you can see that each of these values is going to correspond to one of the betas. So we have beta 0, beta 1, beta 2, beta 3, beta 4. Beta 5 we want to take as a 1 because our first hypothesis is beta 5 equals 0, and then 0, 0. And then we're going to have the same thing going on for these next values as well. So that's going to be a 0, and then beta 6. And then we'll zero this one out and put a 1 on beta 7. Okay, and now if I call this, and then I just take a look at L right here, you can see L is just this matrix that has a 1 in these 3 columns. And so if I take L times beta hat, well, then what we're going to get is sort of that estimated vector that corresponds to this joint hypothesis. And so what I'll do is I'll say define beta hat to be the coefficients, coef, of our saturated model. Okay, so we've defined beta hat. We also need the variance, and so I'll call it variance of beta hat. And you can get this by calling model saturated $, and then in the $, we want the variance of beta, or var beta. Okay, so if I take a look at that, you can see that we have this really big matrix because the text is quite large, but it's the matrix of the variance matrix for our estimated beta hat. Okay, so now what we want to do is we want to take a look at sort of that quadratic form that we had set up. And so to do this, we said that we took L times beta, and so I'm going to define this LB, which is L matrix multiplication, which we get by percent sign asterisk percent sign, so L times beta hat. And then we looked at this quadratic form in terms of the last lecture. And what we did for that one is we had L beta hat minus L beta transpose times by the inverse of the variance, and then L beta hat minus L beta total. And so I should really be calling this L beta hat, right? Because that's what we're actually looking at there. It's computed using beta hat. And so to get our test statistic, and maybe I'll just call the test statistic W, what we want to do is we want to take L beta hat minus L beta. We're going to take this transpose. I'm going to multiply this by the inverse of this matrix. To get an inverse matrix in R, we use solve. And in particular, we actually need to multiply this by the L and L transpose on either side. And then we want to matrix multiply this by L beta hat minus L beta. Now, L beta here, this is going to be the L times beta under the null hypothesis. So if our null hypothesis is true, L times beta should be equal to a vector with 3 zeros, because that's what our assumption is if our hypothesis is true. So I'm going to do 0, 0, 0. And then I will run this and see we should get W, which is a single value, right? So again, I advise you to take a look at those slides that I've posted on the course website and see how this corresponds to that test statistic. But once we have this, we know that this is going to follow a chi-square distribution where the rank is equal to the number of degrees of freedom is equal to the rank of this test. And so in this case, the rank is 3 because there are 3 rows here. And so to get a p-value, we can say 1 minus p chi-squared, and we want to pass in our test statistic, and degrees of freedom equals 3. And if we take a look at the p-value here, we should find that it is effectively 0, right? Which corresponds to the exact same p-value that we saw when we used ANOVA. But this way, let us sort of ask a more flexible question. So as a general rule, that's sort of the idea with using GLS in this context to fit these marginal linear models in this way. Now, if you actually want to start thinking about the estimation of variance and correlation parameters, right, and you want to estimate those ones with as little bias as possible, then we would want to update this method to be the restricted maximum likelihood. And it's as simple as doing that. You can run this and you get the same situation here. And then the only other point that I want to make here is that so far we've been assuming that the weak is going to be a factor variable, right? And so we had talked a little bit about this at the beginning. And if you remember the plots from this data when we were first looking at it, it looked like the trend was all over the place. But you could, in theory, fit this same model where we don't assume that these are a factor variable. And so if I come up and I just grab my code for the model saturated here, and I come back down, we can do a continuous time variable here. So I'll call this model continuous time. And instead of calling factor of week, we're going to just do it based on the week. And this isn't actually going to change anything. I think that should all be okay. We'll fit using maximum likelihood. We run that. And now if we actually call the summary of the model continuous time, now if we scroll up to see our coefficients, you can see now we've only estimated 4 coefficients, right? So we're only estimating a single coefficient for the week parameter here, all right? And so what we're really saying is that now, as weeks are increasing by 1, we expect the average to drop by this much, so to drop by 0.538, and if you're on the placebo, then it's to drop by 0.538 plus this 0.17 here, right? So that's a linear trend in this model. If a linear trend didn't seem appropriate, perhaps we'd want to fit a quadratic trend instead. Then we also could have used sort of a quadratic model. And so maybe I'll come in here and I'll say model quadratic down here. And I'm going to grab this code here, paste it in, and I'll show you what we're doing with this. So what we want to do here is pull this all over so that it's all very sort of more legible, and then talk through it. So we have this quadratic model, and we're now saying W is going to be equal to week plus week squared, okay? And then week plus week squared interacting with treatment. All right, now there's this interesting choice that I've sort of illustrating with using this formula here. And so if I run this quickly, and then I take a look at the summary of model quadratic, you can see that when we've estimated this here, we haven't estimated a main effect of treatment, okay? And if I scroll back up to the model that I just fit, we did estimate a main effect of treatment, okay? And so sort of what's going on there? Well, the idea would be that if you're going to treat time as a continuous variable, right? So if week is continuous, then at the baseline, at week equals 0, if the people have not been randomized to their treatment yet, we wouldn't expect there to be any difference between placebo and active treatment. And so because of that, this treatment indicator, when we're treating time as a continuous variable, becomes a little bit hard to interpret because at sort of week equals 0, there's not going to be this fixed effect. And so in fact, this interaction is typically what we actually care about. And so down here, we can see that in the quadratic model, we haven't fit a main effect of treatment. And so now instead, week is interacting with the treatment and the week squared term is interacting with treatment. I'll also note that you can see that in this formula, I've passed week squared in this I function. What that's going to do is actually evaluate this term so that you don't have to define this in your data frame directly. And so if you ever want to pass in a functional form in an R formula, wrap it in this I function and you'll get that. Now, implicitly, there would be nothing wrong with including the main effect of treatment here. And so if I now look at the summary of the model quadratic, we should see that, it will estimate all of those effects. So now we have this, this main effect of treatment right here. But the idea is that generally speaking, from a scientific perspective, if we're actually thinking about this, at week 0, we want those two groups to be indistinguishable. And then after week 0, we start to treat them. And so with this continuous time interpretation, it becomes a little bit more suspect to include that main effect unless the two groups were different to start, right? If the one group's receiving treatment because they already had higher rates of lead and the other group's receiving a placebo because they already had lower rates of lead, then it makes sense to differentiate them at baseline. But otherwise, that might not make so much sense. Okay, so those are sort of the core ways that we would go about fitting the models here. I actually already talked about the correlation patterns sort of early on. And I guess the last thing to point out is that sometimes you're going to want to I would suggest that you all want to sort of play around with fitting all sorts of different types of models here, right? So I've gone through just a few, I've tested a few hypotheses, but you could think about sort of asking any question of these data and then trying to come up with an answer for it using these methods that we've showcased. So this nested method of testing hypotheses is incredibly powerful for testing different scientific questions, right? So what if instead of a compound symmetry assumption, we assume some sort of decay, right? So if we assumed a Gaussian or an exponential or an AR1, right? How would that look? What about other hypotheses tests other than the time trends being the same between the two groups. Maybe we don't care if the full-time trend is the same, but maybe we just want to know perhaps the first week is different, and then after that they're the same. And so what would that look like? How could you adapt all of this code to do that? I would really highly advise you to go in, to take a look at this code, to take a look at the data, to modify it, to ask questions of these data, to try to get your sort of hands dirty and understand how can we use this nesting of models to answer scientific questions, because that's largely what we're going to be doing in this course. So I hope that that sort of made sense, that syntax makes sense, and that gives you something to start playing around with. And I will see you all in the next lecture video.